Okay, so when we last left off, we talked about many methods to prepare and generate ethers. So silver oxide, the way that I want you to think of silver is that silver serves, or more correctly, silver salts in general, silver 1 salts in particular, activate alkyl halides as leaving groups. Formation of this silver halide salt is a driving factor that helps drive the reaction to completion, in addition to the fact that the silver salt will coordinate and activate your halide to leave. Thus, if you treat an alcohol with an alkyl halide and silver 1 oxide, you rapidly generate the corresponding ether. This method is run under neutral conditions and it eliminates the need to generate an alkoxide. This is really important because it allows you to run reactions to generate ethers under neutral conditions. So you can use this to form ethers of relatively sensitive alcohol substrates. For example, you can take glucose and you can methylate each of the 5 free alcohols on glucose. Does this idea make sense? And does the role of silver in promoting this reaction make sense? Okay, so let's keep going now and let's talk about other methods to generate ethers, one of which is alkoxymercuration of alkenes. Now, oxymercuration can be used to install not just an alcohol, but any alkoxide functionality if you use an alcohol as your nucleophile. So for example, if we replace water with any generic alcohol, you can add an alcohol into an alkene via oxymercuration. So just to showcase an example of this, if you have your typical alkene and you treat it with mercury acetate, and this time, rather than using water, let's suppose what happens if we use methanol. So first we have coordination. We generate our mercurinium ion. Now, just like always, when it comes to the attack of our nucleophile, our alcohol nucleophile, which in this case is methanol, will attack with Markovnikov regio control. The alcohol will add to the most substituted carbon that can most readily stabilize a cationic charge. That in turn will give us the following product. And then of course we can burn off the mercury in a separate reduction step. So oxymercuration allows you to prepare not just alcohols, but it allows you to prepare ethers by using an alcohol as your solvent. Does that make sense to everyone? Yep. So from here, just to generate a neutral species, the alcohol proton can be removed by solvent. So for example, or acetate for that matter, either would work in this case. We can draw it with acetate removing the proton. Very good point to bring up. Does this idea and this method to prepare ethers make sense? So oxymercuration of an alkene using an alcohol as your solvent allows you to prepare ethers with Markovnikov regio control. To show another example, one common modified reagent that's used for these alkoxymercuration reactions is mercury trifluoroacetate. Now, one benefit of mercury trifluoroacetate is it's a much more reactive mercury-based electrophile. The reason for that is your trifluoroacetate groups are extremely electron withdrawing. So mercury trifluoroacetate is commonly used in cases where you have a relatively unreactive alkene. So in this case, if we use methanol as our solvent, we'll attack and open our mercurinium intermediate with Markovnikov regio control. In this case, we're attacking the more substituted secondary position, and it's a benzylic position. So it's even more favored when thinking about Markovnikov regio selectivity, because it's very easy for us to stabilize a cationic charge at this benzylic position. That in turn gives us the following ether and a carbon-mercury bond, which is reduced off upon treatment with sodium borohydride. So mercury trifluoroacetate is just a more activated equivalent of mercury 2+. Does this idea make sense to everyone? And is everyone comfortable with the mechanism for this oxymercuration reaction? Any questions? Okay, so let's practice what we've learned, and let's draw a mechanism for the following reaction and predict the products of the following reaction. And notice we're just dealing with the first step, the alkoxymercuration step. So let's take about 3 to 4 minutes and let's try to predict the product from this reaction and draw the mechanism for this reaction. So let's keep working through this example. And if you'd like, you can share your proposed mechanism in the chat. You can explain the steps verbally. Or what you can do is you can also try to draw out and annotate your proposed mechanism on the class whiteboard. This is a textbook alkoxymercuration reaction, and the substrate's pretty carefully chosen to avoid issues associated with stereo control. So would anyone like to try to share the mechanism for this reaction using the annotate tool? Or would anyone like to share a photo of their written work for this mechanism in the chat? If you have questions as well as you draw out the mechanism, I'd also be happy to provide my feedback and input. So does anyone have any questions or comments as we work through this example?
Professor, can I have a question?
Yes, please go ahead.
Will the alkene react with the mercury?
Yep.
Okay.
So and how would that look in terms of an arrow pushing mechanism?
The pi bond will go to Hg.
Yes. Okay, so drawing out mercury trifluoroacetate. Yep. So the pi bond will attack our electrophilic mercury atom. Okay, and what happens during this process? So our pi bond attacks our electrophilic mercury atom. And what happens as part of this concerted first step?
Wouldn't there be also an arrow from Hg to the alkene?
Yep, we end up with attack to generate our cyclic mercurinium intermediate. Okay, what else happens when our alkene attacks our electrophilic mercury atom?
Are there lone pairs on Mercury, or like where are the electrons coming from?
So in terms of where the electrons are coming from in this case, Mercury does have some electron density located on the mercury atom. However, it's best thought of as, so you have your pi bond and Mercury is coordinating to that pi bond. And so we're distributing some of that electron density that was originally held in our pi bond to our two bonds to our Mercury atom. Does that make sense?
Wait, okay, could you say that one more time? Like how?
So it's your Mercury atom coordinates the pi bond, and we're essentially distributing the electron density found in that pi bond into our two sigma bonds to Mercury.
Oh, okay.
Does that
So
make sense?
yes. So then, to answer your previous question, well, one of the acetates will leave.
Yep, exactly right. Because Mercury can only has a certain number of available sites for coordination. Yep. So we generate our cyclic mercurinium ion with one trifluoroacetate group still remaining. I'm just arbitrarily showing the mercurinium coordinated on the bottom face. So now what's our next step? Let me draw that down here just so that way we can draw the product in its own unique spot. Okay, so we've generated our cyclic mercurinium ion. And now what's our next step? Would anyone like to annotate or verbally describe the next step? So we have our cyclic mercurinium ion. We have a relatively electrophilic species. Do we have an available nucleophile? What's our nucleophile in this case?
Would it be the OH?
Yep, our alcohol. Okay, so we have our alcohol. And now where will the alcohol attack? So in oxymercuration, which site is preferred? So what site is preferred under Markovnikov regioselectivity? What site is the more substituted site? So I'll label them carbon A and B. So which carbon gets attacked as we open up this mercurinium? A. Yep. So we attack, we open up our mercurinium intermediate. This attack follows Markovnikov regio control. And now really importantly to note, when we open up our mercurinium intermediate, the alcohol attacks from the opposite face. So anti-stereochemistry, Markovnikov regiochemistry. Okay. Okay, so that gives us our addition product. And now as a last cleanup step, another equivalent of alcohol or an equivalent of acetate will pull off our proton. In this case, it would be trifluoroacetate. And that gives us our neutral species. Plus the enantiomer. Does this mechanism make sense to everyone? And does our predicted product make sense to everyone? Any questions on this example? Mercury acetate would work, but mercury trifluoroacetate is often used as it accelerates the rate of this reaction, because mercury trifluoroacetate is substantially more electrophilic. Does that make sense? Yeah, you can run, these reactions are typically run at room temperature or low temperature. They don't necessarily need to be heated or anything like that. It's a relatively efficient reaction. Any other questions I can address? Okay, so let's keep going then. Let's talk about a common reaction of, let's talk about a common reaction of ethers under acidic conditions, which is the acidic cleavage of ethers. Ethers are generally unreactive. However, treatment of an ether with strong acid at high temperatures will cleave the ether and install an alkyl halide. Hydroiodic and hydrobromic acid produce the alkyl halide at the least hindered or the less hindered position. This occurs via an SN2 reaction for primary and secondary ethers, while ditertiary ethers undergo an SN1-like reaction. So for example, if you have ethyl phenyl ether and you treat it with hydrobromic acid, in our first step, we protonate the ether. That in turn will generate a more activated leaving group. From there, your nucleophile of bromide is going to attack the less substituted position where you can actually see displacement. This is one of the few cases where we have an SN2 reaction run under acidic conditions. So which carbon, A or B, is preferred for displacement? Which carbon is easier to attack? Which carbon can facilitate, and which carbon is permitted for an SN2 reaction to occur? Carbon A or B? B, exactly right. You can't have an SN2 on an sp2 center. Okay, so that gives us our two products of phenyl and bromoethane. So when we think about viable acids for this reaction, would anyone like to comment, why is hydrochloric acid not preferred? Why is hydrochloric acid not used for this reaction? And think about the second step really carefully. So why is hydrochloric acid not usable for this reaction? Chloride is not as good of a nucleophile. Exactly right. Chloride is a very weak nucleophile. And as a result, it's not sufficiently strong enough as a nucleophile to displace this leaving group effectively. Further, hydrochloric acid is generally a weaker acid compared to hydrobromic or hydroiodic acid. So these two factors make it so that if you want to displace an ether and cleave an ether under acidic condition, you have to use hydrobromic or hydroiodic acid. Does that make sense to everyone? Does this idea make sense? Does everyone understand why we're limited to hydroiodic and hydrobromic acid? Okay, so to reiterate this idea of regioselectivity, if you have an ether with two possible sites of reactivity, a tertiary and a a tertiary in this case. No, sorry, that's secondary. Secondary versus primary position. Your halide will attack and displace your leaving group from the less substituted position. So we'll attack the less hindered position, and as a result, we'll generate a highly substituted alcohol and a relatively unsubstituted alkyl halide. Does this idea of regioselectivity make sense? It is still an SN2 reaction at the end of the day, and SN2 reactions are fastest on primary substrates and are slower on secondary and tertiary substrates. So under SN2 conditions, your halide will prefer to attack the least substituted or least hindered position. Does that idea make sense? Okay, perfect. So when you have a tertiary benzylic or an allylic ether, rather than operating under the SN2 conditions, ether cleavage occurs via an SN1 or E1 mechanism. So for example, if we have tert-butyl cyclohexyl ether, so we have a tertiary and a secondary site, and we treat it with trifluoroacetic acid. It's a pretty strong acid. So as our first step, we're going to protonate our ether. That in turn generates an activated leaving group. Now from there we have a few choices, but the first step in either the SN1 or E1 mechanism is the loss of our leaving group. Now if we had to pick to form a secondary or tertiary carbocation, which carbocation would we form? Which carbocation is more stable?
Tertiary.
Yep, exactly right. So in our first step, our leaving group leaves. So we get our secondary alcohol with no issues. And then from there, when we have a tertiary carbocation, there are two main options for our tertiary carbocation. The first of which is our tertiary carbocation is just attacked by water or another nucleophile, and that generates a highly substituted alcohol. The second option for our tertiary alcohol, or in this case, our tertiary carbocation, is that we can then eliminate a proton to generate an alkene via an E1 mechanism. So, in this case, ether cleavage under acidic conditions for highly substituted ethers occurs via a mixture of SN1 and E1 mechanisms. So we see a little bit of the SN1 product, we see a little bit of the tertiary or other highly substituted alcohol, and we see a fair amount of elimination, which is why we see 2-methylpropene as one of our products from this reaction. Does this mechanism make sense?
So what prompts the elimination of the tert butyl group? Like, does it just happen, or?
So once you have this protonated intermediate, the first step in either an SN1 or E1 reaction is loss of the leaving group. So because we have a relatively good leaving group, and loss of this leaving group would yield a relatively stable carbocation, loss of our cyclohexanol leaving group occurs quite readily. There is still a barrier. However, once you generate the carbocation can rapidly react via elimination or SN1 substitution pathways to yield the alkene or tertiary alcohol. And those products are substantially lower in energy, such that you don't often see a reversible reaction. Of course, this tertiary alcohol and the alkene are in equilibrium, but usually these reactions are run under relatively dilute conditions, so you don't see attack of cyclohexanol onto your carbocation. You usually have water or solvent available, and such a large excess of solvent available such that you'd rather see this tertiary alcohol rather than just reversion back to your reactant. Does that answer
Okay.
your question?
Yes, thank you.
But yes, these steps are technically reversible. Any other questions on this example? Okay, so let's keep going then. So let's try to draw a mechanism for the following reaction. And is something off with this reaction already? Is there a problem with these conditions?
The HCl,
Yeah, and what's a problem with HCl?
it's a weak acid and a weak nucleophile.
Yeah, and it's the nucleophilic character of HCl that's most important. Chloride is a terrible nucleophile for the most part. So let's use a more viable nucleophile. Let's use hydroiodic acid, or HI. Okay, so if we treat the following ether with hydroiodic acid and water at high temperatures, let's try to draw a mechanism for this reaction and predict the products for this reaction. And in this case, you may get a mixture of products. So let's take a few minutes and try to draw the mechanism for this reaction. And don't be shy to share your responses as a photo of your mechanism in the chat. You can also directly annotate and draw your mechanism on the class whiteboard, and you can certainly ask questions in the chat or verbally. So in our first step, our ether is protonated. Yep, that's exactly right. So let's draw out that protonated intermediate. So we protonated our ether. Oops, one more carbon there. Okay, so now what happens next? We have some iodide floating around. So where does the iodide attack and what products do we observe?
I would assume it would attack the carbon to the right of the oxygen
Sure, and
because
what
it's
is,
less hindered.
yes, it's slightly less hindered, exactly right. You do see a mixture, but there is a preference to attack this carbon on the right because it's away from
Because they're
this.
both secondary, right? Or
Yep, exactly right. We have two secondary positions, but the position on the right is less hindered because we don't have this giant bulky cyclohexyl group getting in the way. Exactly right. So we attack our least hindered position. That gives us our alcohol. And it gives us our desired primary alkyl iodide. Yep. Another byproduct that we could potentially see can be formed if we attack at the other position. Although this is a minor product, the difference in steric hindrance is not large enough that you'd get complete selectivity. So your iodide could very easily just attack the other quote unquote secondary position, and that would give us the following primary alkyl iodide as well as a primary alcohol. So we do see a mixture with the first set of products being the major product. Does that make sense to everyone? Any questions on this example? Yeah, so one thing I want to correct, the student mentioned that these are secondary, but these are primary carbons. And that's part of why we see primarily SN2 pathways over SN1. Any other questions on this example? Yep, no worries. Okay, so let's keep going then. And this time, let's try to draw a mechanism for the following reaction. Not much has changed, but a lot has changed for this substrate. In this case, hydrochloric acid is sufficient. And I'd like you to think about, why is hydrochloric acid suddenly okay for this reaction? So let's take a moment. Let's try to draw out a mechanism for this reaction. And I'd like you to share your questions and proposed responses in the chat, verbally, or annotated on the class whiteboard. And in this case, we can use hydrochloric acid, and I'd like you to think about why that is. Does anyone have a proposed mechanism, or does anyone have a question on this example as we work on drawing the mechanism and predicting the products for this reaction? You can also share your responses or any questions in the chat or verbally, or you can try to annotate your responses on the class whiteboard. Would anyone like to share their proposal? So we have one student commenting that we'd see a mixture of SN1 products with benzyl chloride being the major product. Okay. So to showcase part of what that student is trying to convey and what they shared in the chat. So on our first step, we'd protonate our ether. And now this is really interesting now. Once we have our protonated ether, we have two choices. We have a primary benzylic site or a primary allylic site. And which site gives us the more stable carbocation? Which carbocation is more stable? Benzylic, exactly right. So our leaving group is going to leave, and we're going to generate a benzylic carbocation. It looks less stable than it is. This is a very stable carbocation. Now from there, and this is the beauty of this substrate, what's special about this substrate? So we can either have SN1 or E1 pathways, though it's a little odd for me to say E1 pathways, because what's very special about this substrate? Do we see any E1 pathways? Do we see any elimination? We don't see elimination because there are no adjacent protons for elimination to occur. So as a result, when we have this nucleophile, chloride is a terrible nucleophile, but anything will do when it comes to reacting with a carbocation. So we'll attack our carbocation, and that in turn gives us our two principal products from this reaction, which are benzyl chloride and allyl alcohol. So does everyone see why chloride is viable in this case? Does everyone notice because we're going through an SN1 mechanism, any remotely competent nucleophile is usable? Well, if we're dealing with an SN2 mechanism, we need a nucleophile that is reasonably strong to displace our leaving group.
So in the previous example, you just drew the iodine like directly attacking the primary carbon. In this case, the carbocation formed first.
Yes, that's exactly right. And that's a critical distinction.
Okay, that's why we could use
in this case, we have a substrate that's benzylic or allylic. So as a result, we can generate a very stable carbocation. Thus, the reaction proceeds through an SN1 mechanism rather than an SN2 mechanism. Does that make sense?
Yes, thank you.
Perfect. Any other questions on this example? Okay, so let's keep going then. And this is a very important reaction when it comes to generating substituted phenols and substituted anilines. And this is a reaction specific to allyl aryl ethers. So if you take phenol and you alkylate it with allyl bromide, you generate an allyl phenyl ether. Heating this allyl phenyl ether or allyl aryl ether at high temperatures generates an orthoallyl phenol. This is our first example of a sigmatropic rearrangement. And this is called a 3-3 rearrangement, designated by the fact that if you look at the bonds that we're forming and breaking, we're forming a bond and breaking a bond at position 3 relative to each of these fragments. We'll talk more about sigmatropic rearrangements later on in this course, but this is our first showcase of sigmatropic rearrangements under thermal conditions. So this reaction is known as a Claisen rearrangement, and it's used to prepare orthoallyl phenols from allyl phenyl ethers. To unpack the mechanism a little bit for this sequence, suppose that you start with a phenol. Okay, we treat it with sodium hydride. Let's use sodium hydroxide just so that way we can draw out the arrow pushing mechanism for this deprotonation step. We generate our phenoxide anion. We then treat it with our allyl bromide, and these can be substituted, but generally you like to use simple allyl bromides just to avoid issues with getting the actual Claisen rearrangement to go. Okay, that in turn generates our allyl phenyl ether. Now let me draw our double bonds in the right spot. And from there, upon heating, this initiates a 3-3 sigmatropic rearrangement. Now, the book actually skipped a step, and this is important to note. From the first step, we don't directly generate a phenol. We generate an alpha allyl ketone, right? However, is this ketone going to be isolable? Would we ever be able to isolate this ketone under practical conditions? Not just unstable, but you can easily tautomerize this ketone to yield an aromatic phenol. So this ketone's not going to be sticking around for very long because you can immediately tautomerize to phenol. And again, the aromatic system is way more stable. So in the end, we're able to isolate an alpha allyl phenol. And what's important is that we only see the ortho substituted product. We don't see any of the para product because this Claisen rearrangement occurs via a concerted 3-3 sigmatropic rearrangement. We can only rearrange and move our allyl group to the ortho position. This reaction is regioselective to install the allyl group at the ortho position. The para product is not observed in the Claisen rearrangement. So this gives it a unique benefit compared to, for example, Friedel-Crafts alkylation. In addition, this reaction is easy to control the chemoselectivity because the chemoselectivity is controlled by this first alkylation step. Does this idea make sense to everyone?
Could you draw the arrow for the second step where you go from, we have the
Ah,
negatively
yes, sorry.
charged oxygen?
Yeah, sorry about that. That's just a typical SN.
Okay.
One thing I would like to bring up is that you can also see the Claisen rearrangement you can also observe Claisen rearrangements for systems that are non-aromatic. So for example, if you have a substrate like so, and you heat this substrate to high enough temperatures, you can in turn trigger a 3,3 sigmatropic rearrangement. In this case, you would get a genuine alpha allyl ketone. Let me draw a methyl there just to avoid introducing another issue. So the Claisen rearrangement applies for both aromatic and non-aromatic systems. And there are many variants of the Claisen rearrangement. Does that make sense to everyone? Does this idea make sense? Any questions? Okay, so let's keep going. And just to refresh our idea of the Claisen rearrangement mechanism, it's a concerted pericyclic 6-electron mechanism involving a 6-membered ring transition state. It's a 3,3 sigmatropic rearrangement, and it's similar to that of the Diels-Alder reaction. I'd want you to note that we generate an intermediate alpha allyl ketone that tautomerizes to the phenol. And really important, this occurs under thermal conditions. Okay, so just a brief aside on some common solvents. Cyclic ethers are very common solvents utilized for a range of reactions. They're really useful as polar aprotic solvents, useful for Grignard reactions, for example. And cyclic ethers generally behave like acyclic ethers, except if the ring is 3-membered. Common solvents include dioxane and tetrahydrofuran. 3-membered rings, which are known as epoxides, have unique reactivity, as we've already seen. Any questions on cyclic ethers? Any questions on cyclic ethers? Okay, so let's keep going then. And let's talk about epoxides, also known as oxiranes. Now, when we think about epoxides, there are a few naming conventions. The 3-membered ring, this 3-membered cyclic ether, is known as an oxirane. Also known more commonly as epoxides. Now, there are 2 methods to name epoxides. The first method under IUPAC, the oxygen atom is treated as a substituent on the parent chain. So you name the parent chain as the longest chain containing the epoxide functional group. You indicate the location of the epoxide using the locant numbers for the 2 carbons bonded to the epoxide oxygen. Finally, you add the epoxy prefix after the epoxide locant numbers. So in this case, for example, we'd number the epoxide as a substituent. We'd try to give the epoxide the lowest possible locant numbers. So in this case, we'd call this 3-ethyl, 2-methyl, 2,3-epoxypentane. Notice how both of the locant numbers for the epoxide are noted clearly. Does that make sense to everyone? Okay. The second method is to treat the epoxide as the parent chain. In this case, you name each substituent attached to the epoxide ring. You assign locant numbers for each substituent, starting with oxygen at locant number 1. The parent epoxide ring is named using the oxirane suffix. So for example, in this case, the epoxides are parent chain, so we name it 1, 2, 3. Would anyone like to comment why I use the following numbering arrangement rather than this alternative numbering arrangement in red? So you have a methyl group and an ethyl group. Why do we choose the numbering method in black? So we're assigning locant numbers. We want to give the lowest locant numbers as possible. The epoxide is the parent chain. Yep. But why are we numbering ethyl lower than methyl? As students are noting in the chat, it's based on alphabetical, right? Ethyl E is first before M in methyl. So if there's a tie between priority, you assign the lowest locant number to the first species in alphabetical order. So this would be 2,2-diethyl, 3,3-dimethyl oxirane. Does that make sense? Perfect. Did someone have a question? I just noticed someone is unmuted and I just want to make sure I'm able to hear if they have a question. Okay, so let's try to apply what we've learned now.
Wait, I have a quick question.
Yep. Go ahead.
So I'm just like thinking this through. So you could only really ever have 2 substituents on each of those, right? Because there's only like the oxygen is 1, and then it would be 2 and 3. Like there wouldn't ever be any more.
That's correct.
Okay, just making sure.
Both are acceptable. Both naming methods are acceptable. It just depends on the compound. In some cases, it may be easier to name the epoxide as a substituent. In other cases, it may be easier to use the oxirane as the parent chain. And we in fact have 2 examples that demonstrate that. These 2 examples each have an easy way to name the compound and a more difficult way. So,
Professor, I have a question.
Yes, please go ahead.
So how do you know which method is going to be like preferred for what compounds? Like, or
It really depends on the compound, the substitution pattern, and what substituents what naming conventions you're comfortable using. IUPAC accommodates both the oxirane and epoxy naming conventions.
okay.
So
Alright.
there's not really a definitive answer. It really comes down to preference. Generally, if your substituents are simple, it's easier to name it as an oxirane and name the substituents as substituents. If you have a more complicated molecule that contains an epoxide, in many cases, you'd have to name the epoxide as your substituent. Does that answer your question?
Yeah, it does. Thank you.
Okay, perfect. So let's try to name the following compounds. I'll title them A and B. And I'd like students to try and name these compounds and propose IUPAC names for each of these compounds. So we have a proposed name for the first compound of 2-isopropyl 3-methyloxyrane. What does the class think of that name? So we have a lot of students noting, yeah, that looks reasonable. I guess my question to all of you is, how is the iso prefix treated in terms of naming? How is the iso prefix treated in terms of naming? Iso is ignored. That's very important. Propyl versus methyl. Does anyone have a revised name for this compound?
So then it would be 2-methyl-3-isopropyl-oxyrane.
Yes, exactly right. 2-methyl-3-isopropyl oxyrane. Yep.
Would another name be 2,3 epoxy? Oh wait, no, the epoxy comes last. So 4-methyl 2,3 epoxy pentane.
Yes, exactly right. And it's important to be familiar with the epoxy substituent naming convention, because you may have structures where the epoxide is a minor substituent. It's not very common, but it does pop up. Perfect. So let's take a look at structure B, and let's try to propose a few names for structure B. And I would recommend using the oxyrane naming convention for structure B.
Professor, I have a question.
Yes, please go ahead.
So when using the oxyrane method, we start the counting from the epoxide itself.
Yeah, from the oxyrane oxygen. Yes, that's correct.
Okay, thank you.
Mhm. So we have a proposed name of 2-methyl-2-benzene oxyrane. What do we call this substituent? Rather than benzene, what's the name for this substituent? Would anyone like to provide a revision? Toluene or a toluene group would look something like this. What do we call just a typical, in isolation, this would be a benzene ring. We call this a phenyl group. So it would be 2-methyl-2-phenyl oxyrane. So this group is known as a phenyl group. Yeah, exactly right.
Would you switch the methyl and phenyl or no?
What is first alphabetically? M or P?
Oh, never mind.
Yeah, since P is second alphabetically, the phenyl is named second in the name. But your point to really be attentive towards the order of substituents in the name, that's really important. but that's a really good question to ask. Any other questions on this example?
Would you mind numbering the?
Sure, yes.
Thank you.
So we start with 1 on the oxirane oxygen. To answer the question in the chat, a phenyl group is attached directly to the aromatic ring, while a benzyl group is attached at a methylene group attached to the aromatic ring. Did I answer the questions both in the chat and posed verbally? Did I address everyone's questions?
Yes.
There's a big difference comparing benzyl chloride to chlorobenzene. One's a very strong lacrimator, the other is relatively harmless. Okay, so let's talk about some methods to prepare epoxides. The first of which is the peroxy acid method. The most commonly used peroxy acid is metachloroperoxybenzoic acid, or MCPBA for short. So the mechanism for peroxy acid epoxidation is a concerted one-step mechanism. So our alkene attacks the electrophilic oxygen, and there's a cyclization back on to the second alkene carbon to generate our desired epoxide. Epoxidation is installed with syn stereochemistry. Both of the bonds to the epoxide are on the same phase. Other common peroxy acids that you may see written out or used, but are practically never used in the laboratory unless you really have to, because they're somewhat jumpy and reactive reagents. One example of this is peracetic acid, which is a more reactive variant of a peroxy acid. Does this mechanism look familiar to everyone? This was covered previously as well in Chem 112. Okay, let's keep going then. One other way you can make epoxides is from halohydrins. So if you treat an alkene with a halogen in the presence of water, you make what's known as a halohydrin. Treatment of the halohydrin with base results in an intramolecular cyclization to generate an epoxide. This can be thought of as an intramolecular Williamson ether synthesis. One thing I would like you to note is that this reaction can occur via both an SN2 or an SN1 pathway. And the beautiful thing about this reaction is that the alcohol already embedded in our molecule controls the stereoselectivity. Because by definition, your epoxide must have both of its carbon-oxygen bonds on the same phase. Pretty cool, right? Does everyone get that point? Like, you never can have something like this. This doesn't exist. An epoxide with two of the carbon-oxygen bonds on opposite faces, that doesn't exist. So the stereochemistry of your carbon-oxygen bond controls the final stereochemistry of the epoxide. And if you don't believe me on that first statement, you can try making a model of that epoxide. Just make sure that you are careful with it, because you'll likely break your model kit trying to make that epoxide. Okay, so we can make epoxides via halohydrin formation and treatment with base. let's try to verify and let's try to just make sure we're comfortable with each step in this mechanism. And I'd like us to draw a mechanism for each step in the following reaction sequence. In the first step, we're generating our halohydrin, and in the second step, we're closing our halohydrin to make an epoxide under basic conditions. So as we work through drawing the mechanism for this reaction, I'd like students to share their proposed mechanisms in the chat, verbally, or as annotations on the class whiteboard. The first step is a refresher that we've seen previously in the chapters on the synthesis of alcohols and the synthesis of ethers, and we've also seen it previously in earlier organic courses. So would anyone like to start drawing out the mechanism for this reaction? And please include the stereochemistry for your intermediates and your products. So would anyone like to share their proposed mechanism? Yep, the first step, we cyclize our alkene onto our electrophilic bromine atom and form a bromonium intermediate. So our alkene attacks our electrophilic bromine atom, and bromine cyclizes back onto our second alkene carbon, and that in turn generates our bromonium intermediate. We'll arbitrarily draw it on the bottom face. From there, we have water. So where is water going to attack? What is the regiochemistry and stereochemistry? So will we attack at carbon A or B? Keeping in mind that when you open a bromonium intermediate, it follows Markovnikov regiocontrol. So which site gets attacked, A or B? Let's try to get a few responses from the class. Site A is exactly correct. It's the most substituted site that can most readily stabilize a positive charge. And in terms of stereochemistry, if our bromine is on the bottom face, what face is the alcohol installed on? It'll be on the top face. Exactly right. For halohydrin synthesis, it follows Markovnikov regioselectivity for installation of the alcohol, and it follows anti-stereoselectivity.
So will the, oh yeah, I was gonna say, will the methyl be pushed back?
Yep.
But you drew it. Okay.
From there, we have a cleanup step where we pull off a proton. Markovnikov selectivity is your nucleophile or group that is installed will be installed at the most substituted position that can most readily stabilize a positive charge. Does that answer your question?
Yes, thank you.
Okay, so now that we have the following intermediate, if we treat it with potassium carbonate, what's going to happen next? So would anyone like to continue on with this mechanism and share the next steps for this mechanism? Oh, yep, that should be a methyl.
So the alcohol will be deprotonated,
Yep, in the first step, the alcohol is deprotonated. And you
and
don't
then
even, yep, please
and
go ahead.
then the arrow will be drawn from the negatively charged oxygen to the carbon with the bromine.
Yep, so this is like an intramolecular SN2 reaction. In some cases, you may also see an intramolecular SN1 reaction if you have a tertiary position. Okay, and now for a really important question and something you should be considering at all times. Do we make a mixture of enantiomers in this case? Do we make a mixture of enantiomers? So
I would say yes, because we arbitrarily chose to install it on, or to install the bromine on the bottom at the beginning.
yep, when it can just as easily be installed at the top phase. Exactly right. So writing plus enantiomer is appropriate in this case. And the second check that you need to do is the substrate's not symmetrical via rotation. So you do have a genuine set of stereocenters, and your enantiomer is actually non-superimposable. And just to draw that out so everyone can see that, this structure for our enantiomer is non-superimposable. Does that make sense to everyone?
And so by non-superimposable, you mean that they're not the same molecule, or
Yeah, they're not the same. There's a different configuration at each of our stereocenters.
Okay.
And we can prove that by noting that this stereocenter is R, this stereocenter is S, and in this structure, the configurations are reversed. Because this structure is equivalent to these two structures are equivalent. And as we can see, if we look at this center is S and this center is R. Does that answer your question?
yes, thank you.
Perfect, perfect. So, just like we talked about epoxide opening under acidic conditions as a means to prepare transdiols, we can just as easily use epoxide opening under acidic conditions to prepare ethers as well. So epoxide opening under acidic conditions proceeds with Markovnikov regioselectivity and anti-stereochemistry. If the epoxide opening is performed with an alcohol nucleophile, the nucleophile is incorporated at the most substituted position. So this is a wonderful method for preparing substituted ethers. And it allows you to prepare ethers while setting multiple stereocenters. Does this mechanism make sense to everyone? The only thing we've done is we've just elaborated this acid catalyzed epoxide opening mechanism to apply not just to using water, but using alcohols. Does that make sense to everyone? Okay. so let's keep going then. Now, just like we can make epoxides from halohydrons, and just like we can install nucleophiles by treating an epoxide with a nucleophile under acidic conditions, we can synthesize halohydrons from epoxides by treating an epoxide with anhydrous acid. Cross out hydrofluoric. The book mentions hydrofluoric, but fluoride is really not a good nucleophile. And it's so different from these other halogen acids that practically you will not use hydrofluoric acid to form a carbon-fluorine bond in most practical applications. There are better methods to form carbon-fluorine bonds, and there are better fluoride equivalents. Okay, so to talk a little bit about the mechanism, this is just a classic rehash of the acid catalyzed epoxide opening mechanism. And what I want to do now is I want to show this example when we have a more substituted position. So in our first step, we're going to protonate the epoxide. We now have a more activated leaving group. Now, my question to all of you is, which site is going to be attacked by our nucleophile if acid catalyzed epoxide opening follows Markovnikov regio control? What site is going to be attacked? So A or B? A, yep. And this attack occurs with anti-stereochemistry. So then, if our alcohol is pointing up, what will the stereochemistry be for the chloride, for our installed nucleophile? It'll be pointing down, exactly right. So, does this mechanism make sense to everyone? Any questions on this example? So if we don't have any other questions, this is a good stopping point for today. So we'll archive this recording.